Hello and welcome. Today we want to talk about separation of variables. This concept takes advantage of differential equations of the form y prime equal to f of xy, where f of xy can be expressed in terms of two functions as follows: f1 of x multiplied by f2 of y. Well, before we move on, we want to understand what does it mean if we say that the function can be expressed in terms of functions of x and y. This is what I mean with an example to illustrate it. Y prime, let's say it's equal to x squared y. Okay, this is our f of xy. Okay, matching here. Now if we want to express this in terms of a product of two functions where one of them is a function of x and one of them is a function of y, we can separate it in this form. We have x squared, which is a function of x, and we have y, which is a function of y. So separation of variables takes advantage of this particular expression of functions to be solved. So let's solve some examples using this method so that it sticks. It is the simplest we would meet, one of the simplest we'll meet. So I don't expect us to spend so much time talking about conceptualization of it because there is no concept to romanticize about. So let's dive right into examples and see how this is applied. Example 1 says y prime is equal to xy. So let's solve example 1 and then move on to the others. So solution to example 1. 1. Y prime is equal to xy. It is indeed in the form y is equal to f1 of x times f2 of y, because f1 of x is x and f2 of y is y. We can then use the approach. Okay, well, I didn't actually detail the approach to solving it, so let me do justice to that first. We have y equal to f1 of x times f2 of y. I'm dropping the of x and of y so that it can be cleaner. This is what you do. You express it as dy dx as it befittingly is, equal to this times this, and you then divide both sides by the function of y and multiply both sides by dx. So let's do it step by step. If we divide both sides by f2 of y, we should get 1 over f2 dy dx equal to f1. But remember of x. I'll write it at the end so that you don't lose focus. Okay, good. Equal to f1 dx. So now the whole goal of separation of variables is that we would end up having functions of the same variable and the derivatives of the same variable on one side. So for example, we have dy here and we have y here. No x ever appears on the left. And if we come to the right, we have f1 of x multiplying dx. We have xx. There is no y appearing on the right apart from x. So this is the whole goal. This is what the separation in the separation of variables method is about. You have separated the variables in such a way that you have similar variables of the dependent variable on the left side and similar variables which is of the independent variable on the right side. So that's all, the whole goal of it. When you now get here, the whole skill is for you to be able to integrate. If you can integrate, that's it. So you now have 1 over f2 of y dy equal to f1 of x dx, and then you integrate this with respect to x, integrate this with respect to y, and that will be it. But well, as a physicist, this wouldn't matter much, but I'm going to point it out that the differential operator is not easily, you don't just multiply both sides by the differential operator like that. Around here, what we actually did in reality is this: we integrated both sides with respect to x. So 1 over f2 dy dx with respect to x equal to integral of f1 dx. So we integrated both sides with respect to x, and rewrite this one in a way like this. I'm going to rewrite it here. We have 1 over f2 dy, and we have dx. So the differential of x with respect to itself is still 1. So this becomes a 1. So that's the way to think about it, and not think about it as algebra. The operator is not a fraction. Okay, I want to make that clear. All right, so now that we know how to use the method, let's go ahead and use it to solve the first example. So here we expanded dy dx is equal to xy. Well, we can, since we now know that it is not a fraction and we know all the other procedures, if we are now breaking the rules on doing the shortcuts, there's no problem again, because you are not doing it ignorantly. Okay, so we can multiply both sides by dx right now and divide both sides by y, and we'll get 1 over y dy is equal to x dx. Well, from here, where do we go to? You can take a moment to convince yourself how we get from here to here. Then if we want to integrate, we integrate here, and we get something like, if you're integrating this with respect to y, you should get the natural log of y. And if you're integrating this, you should get, using the power rule, we will have 2 over 2, but you need to add a constant. Well, I need to make another clarification. Okay, but before I make that clarification, let's finish it up. If we make y the subject, we should get something like e raised to the power x squared over 2 plus c, and you are done. You are done with everything needed for this particular problem to be solved. So we have solved this differential equation and we got the general solution for it. If we had initial conditions, then it becomes an initial value problem, and we can find what this c is for that particular initial condition. So what I wanted to clarify is that when you integrate on the right side, let's say you integrated on the right side and you have plus a constant, okay, and you go to the, sorry, that was the left side. So when you integrate the left side, and you get a natural log of y plus a equal to x squared over 2 plus b. Indefinite integrals always require a constant. If you still do this, it is valid, okay, but the point is, a constant is a constant. The constants don't have identity, okay, they are just constants. So you can carry this one to the other side, and then maybe you have x squared over 2 plus b minus a. But b minus a is just a constant, so I can put a constant with it. That's why we follow this shortcut of always adding the constant to the right side, because if we add them to both sides, there is no identity for the constants. So we can simply add one constant to the right to take care of both constants, because the difference between them is still a constant, and the sum of them is still a constant. Well, that is it. But as a side note, it is also worth noting that this is not very familiar to somebody who is introduced to the concept at first, will not immediately understand why 1 over y should be integrated to just ln y. Okay, so this is the idea. It started the other way around. Okay, if we have y like this, 1 over y like this, and we try to find the integral of this the normal way, we would end up with y raised to the power -1, because the 1 over y is still the same as this, and we add 1 to that, we get a 0, and we divide that by the 0, so it will now end up being 1 over 0, which is undefined. But the logic as we know it is that the integral is the area under the curve. The area under this particular curve is not infinity, okay, as this thing evaluates to. So since it's not infinity, well, mathematicians found out that the natural log function, if you take the rate of change of the natural log function, it evaluates to 1 over the function inside. Let me be clear about this. It doesn't evaluate to 1 over the function inside. It evaluates to the differential of the function, okay, let's say the differential of the function over the function inside. So let me take a moment to generalize this. Anytime you have a function, let's say you have a function f of x, okay, I mean the derivative of the function, and you have the function itself as a denominator, and they ask you to integrate this, let's say, let me clean this, and you want to integrate it like this, okay, with respect to x. By definition, the integral is natural log of the absolute value of the function itself. And this is what you have to know. This is by definition the integral of functions of this form. So when you see a function, you are wondering whether it's a natural log, and it's a rational function like this, and you're wondering whether it's a natural log, check whether the numerator is a differential of the denominator. And if it is, then you can just conclude that the integral of such a rational function is the natural log of the absolute value of the denominator, which is the function itself. Okay, so let's move on, and if there is any other thing as a side note I would tell you, then I'll tell you. But we are done with question 1. Question number 2 says cosec x y prime equals to y. Okay, let me write it down here. Okay, number 2. Cosec of x y prime equal to y. Okay, well, let's start the solution straight away. I can divide both sides by cosec of x and simultaneously expand this into its other notation to have 1 over cosec x y. Okay, I can divide both sides by y and then multiply both sides by dx. I told you we are breaking the rule again. So 1 over y dy equal to but 1 over cosec is sine. I mean 1 over sine is cosec, so that means 1 over cosec is sine again. So this is what I mean. Good. Now we have it. We can then integrate both sides. We have separated the variables. We have y here, we have y here, we have x here, we have x here. So variables are separated. We can then go ahead with our integration. Well, again, this one is natural log of y plus plus a constant c1, but the other constant on the other side will evaluate with it to give you 1 constant, so you don't need to care about this side. Now, what's the integral of sine? Okay, how you will know this is to map the differentials. You know that the differential of cosine is negative sine. Okay, so that means if you are integrating sine back to cosine, you would have to get a negative cosine, right? So the integral of sine is negative cosine of x, and we add the constant. And so this is the whole solution for the differential equation. So y equal to e raised to the power negative cosine of x plus c. This is the end, okay? just like we ended for the first one. But if you still want to go further, like you could go further by saying e raised to the power c, e raised to the power negative. You can do that for the first one as well, cosine of x. And this one, a constant is a constant, like operation of constants. E is a constant, and its value is 2.71828182804. Like that's a constant value that we all know. So in this case, this whole thing becomes another constant, e raised to the power negative cosine of x. So you could leave it like this, or you could leave it in the previous form. All right, let's move to the next question. Well, I just looked it up. The next question says y prime is equal to y over x. Okay, well, let's not waste time on this one. We know that this means dy dx is equal to y over x. Okay, now we can then do the cross multiplication and division, and we end up getting 1 over y dy is equal to 1 over x dx. Okay, we can integrate both sides, and we'll end up getting natural log of y plus a constant. But I told you the same process, but we'll just add this to the right side, and natural log of x plus the constants. Okay, well, the constant, if you want the constant to enter the natural log operation, the natural log function, you could put it in a natural log as well. Okay, because the natural log of a constant is still going to be a constant, equal to natural log of x plus, let's say c is natural log of a constant called a, and you know that if you have the sum of logs is the log of the product, so log of the product. So this is it. You end up having natural log of y is equal to natural log of ax. If the logs are equal, then that means the arguments happen to be equal. If you don't want to think about it that way, you can take antilog of both sides. So if you take antilog of both sides, you get y equal to ax, and that is the solution to that, the general solution. So here we are just finding the general solutions, not any particular solution. We find particular solutions when the initial values are given. Okay, let's move to the next question. The next question says y prime bracket open x squared minus 1 bracket close equal to y. This one would have to use partial fractions, okay, because, well, I'll tell you soon. So number 4 says that y prime bracket open x squared minus 1 equal to y. Let's separate the variables first. To separate the variables, we would use the usual method, equal to 1 over x squared minus 1 y, and we continue in that same vein. To separate the variables, we have 1 over y dy equal to 1 over x squared minus 1 dx. Okay, so natural log of y, if you integrate this side and integrate this side, you get natural log of y for this side. But for this side, what do you do? Okay, take a moment to convince yourself that this is equal to, you can use partial fractions, okay, and you can set it up like this: 1 over x squared minus 1 is equal to a, let's say a over one of the factors. This is the difference of two squares, so it will be x squared, and the x squared minus 1 will be x plus 1 and x minus 1. Those are its two factors, so x plus 1 and b over x minus 1. And you can cross multiply and find out what the values of a and b are, and you find out that a will be negative half and b will be half. So that is it. Okay, so now we have it here. let me rewrite it here as half of 1 over x minus 1 minus half of 1 over x plus 1, okay, dx. So since this is long like this, let me split the integral. The integral operator is linear, so we can factorize the half out and can also have this inside, and can also split the same thing for this, have the half outside and have this dx. So this is possible because the integral operator is linear. Now let's do the integration. Okay, so for the integration, remember what I told you about a function being the denominator and its derivative being the numerator. In this case, if I differentiate this, I'm going to get 1, and there's a 1 on top here, so this one is a function's derivative over itself. So I know very well that the integral of that thing under there is going to be natural log of the denominator. So half natural log of the denominator. We use the absolute value sign because we don't want the log function getting negatives. If it gets negatives, then the answer will be complex, and we don't like to extend the domain to complex numbers or the range to complex numbers. And this one will be half natural log of x plus 1. The half is common, so we can factorize it out and get half of the whole thing, which is natural log of x minus 1 minus natural log of x plus 1. Okay, now the next step here is to recognize that we have a log minus a log. When you have the difference of logs, then it is the log of the quotient. So we'll take the quotient, half natural log of x minus 1 all over x plus 1, and this plus c should be the integral of this, the right side, this side. Okay, so now that we are done with this side, we can bring our other side, which was natural log of y, to add to it. We can then make y the subject to complete the solution. To make y the subject, we will have y equal to e raised to the power all of this over here. But I don't want to rewrite all of that without simplification. We know from the laws of logarithms that the coefficient is an exponent. So we would have e raised to the power, the coefficient becoming an exponent would be all of that, the argument of the log, raised to the power half. Okay, now plus some constant. The constant is still there. So we can split this and get e to the power c times e raised to the power whatever is here. The half can become a square root. Well, an exponent's half is the same as square root. So we have square roots of absolute value of x minus 1 over x plus 1. So since e is the inverse of the log function, we know that this becomes just the argument up here. So we'll have, maybe let's just say this constant is a, and times square roots of x minus 1, x plus 1. And that is the solution for the differential equation that we wanted to solve. Okay, our next question is question 5, and it is y prime bracket open x minus 1 bracket close equal to y. It was intended to be like this, but not the same as question 4. It was like that before I cleaned the 2. So let's solve this. Okay, question 5. Let me write it here. Y prime bracket open x minus 1. This would be easy. Let's separate variables. Okay, equal to 1 over x minus 1 y. Let's complete the separation of variables, and would have 1 over y dy equal to 1 over x minus 1 dx. We can integrate both sides and would end up getting natural log of y, absolute value of y, equal to the natural log of this. Why? The reason is x, the derivative of x minus 1 is 1, and that is the one on top here. And based on our rule for integrating rational functions to get logs, this satisfies it. So we'll end up getting x minus 1 here, plus some constants. Okay, that's the usual stuff. The next step in this process is to make sure we transform this particular constant into a form that it has a log inside. So let's say c is a constant, a log of a constant. Okay, a log of a constant is still a log, is still a constant. So you should have maybe natural log of, let me use b. Okay, so this is c, and it's still a constant. We just need a constant equal to natural log of the product. Okay, this is what we have in the end. And since we know that when the logs are equal, then that means the arguments in them happen to be equal, we can conclude that y is equal to b times x minus 1, where b is a constant. And that is the final solution, the final general solution to number 5. I left the absolute value signs out of the y as a matter of convenience, but you should be keeping absolute value signs if you integrate with a log. If you have a function's derivative over the function itself, the integral of this particular rational function is the natural log of the absolute value of the denominator, which is the function. So take note. I'll make another video dedicated to showing how to integrate using trigonometric substitution, because it's very crucial here. Imagine you have an integral like this. You end up having an integral like the integral of 1 over square root of 1 minus x squared. You are simply told that the integral of this may be, I don't even remember very well, but I think it's this. You are simply told that the integral is this, but you are not shown the process. So I'll make a video, separate video, talking about integration by trigonometric substitution. And in that video, I also talk about integration by parts. These are general Calc 1 concepts that should be carried over to this. But it is too tempting to leave it at this, because it keeps nudging me that why is it that when you differentiate this, you should get, or why is it that the rate of change of this is 1 over x? Okay, I just hope I have enough time, but let me just, you can search it up if you want to, but I'm going to brush through the steps. Okay, the proof is actually simple. Let's say you have a function y equal to natural log of x, and you want to prove that the rate of change of this function, or dy dx, is 1 over x. first, this is what we'll do. Let's take antilog of both sides, and we'll end up having antilog of this side will just be x. And what will we do? We differentiate through, like we do an implicit differentiation. So if we differentiate this, we'll get e to the power y dy is equal to, if we differentiate this, we'll get 1 dx. Okay, well, let's divide both sides by dx. Okay, it is kind of a violation to say that, but let me say we will divide. That's what we are technically doing. Divide both sides by dx. And subsequently, let's divide both sides by e to the power y, and would end up getting e to the power y. But what did we define e to the power y as? Like, what did we end up getting e to the power y to be? E to the power y was x, so let's put the x there, and we end up getting this. Well, dy dx equal to 1 over x, and this is what we want to prove here. Okay, let me continue the drawing. So this is what the statement we want to prove, and we just finished. So that was what I wanted to add. So thank you very much for watching, and I'll see you in the next video.